In this episode of the .NET 5 REST API tutorial, we continue our path towards deploying our REST API to a production environment by introducing Kubernetes. We will talk about the implications of running containers outside of the dev box with no downtime, and how Kubernetes is a perfect fit for this and the many other challenges of running distributed systems resiliently. Today you will learn why a container orchestrator is needed, what is Kubernetes and which are its basic components, how Kubernetes enables resilient distributed systems, how to stand up a basic Kubernetes cluster in your box, how to deploy your REST API and MongoDB to Kubernetes, and how to scale a Kubernetes deployment. So if you remember from the previous video, we talked about this orange box, which so far we've been talking about. It is the production environment, right? In this case, let's just call it a node. But in the end, this is either the physical or the virtual machine where we're going to be running our Docker engine, right? And it is thanks to this Docker engine that we're able to run a bunch of containers in this node. This could be either our REST API containers or also our MongoDB container or many other containers, right, that we want to run in this node. However, a few interesting questions start arising as we move forward with this approach, right? For instance, who takes care of pulling and running the containers, right? So, I mean, you can imagine that without any further sort of automation, somebody will have to come to this box and actually start doing Docker run for each of the containers that we want to run in this box, right? So that's an interesting question. So either some automation, somebody has to take care of this. How to run the containers, right? So who knows or where is it written all these different environment variables, secrets, and different command arguments that we have to feed into Docker run to be able to run the containers exactly the right way for each of the cases. And what if we don't have enough container instances, right? So what if we need more? So something or somebody has to start spinning up more and more instances as needed, both for our REST API containers or for any other containers that we may have in this box, right? And then also we may not be able to fit we can only fit so many containers in a box, right? So at some point we may need to introduce yet more nodes, right? And then somebody has to decide if the containers that are going to be created are going to go into, in this case, into node 2, node 3, into node n, right? So who decides these things here? So do we have a person that is looking at the different stats for each of these nodes and just decides to do Docker run in each of these machines? How does that work? Also, are the containers healthy? So what happens if one of these containers crashes? What do we do? Who is on point to make sure that we bring back this failed container, and so that we keep having as many as we wanted to start with? Also, where do we store all the secrets? Where do we store the database files for our MongoDB database? Where do we put all this? How do we enable containers to talk to each other, right? Because we know that our REST API containers need to talk to our MongoDB container, but how do we enable that communication? So far we've been using this Docker network, right, to make them communicate, but as we have more boxes, more containers, how do we make sure that they can all talk to each other? And one more thing, how do we reach these containers from the outside, right? Because all of these containers are running in the box, but all of them are running with some port opened locally. But then what if somebody comes from the outside? What would be that public IP that somebody from the outside will use to talk to these containers? And if they talk to them, which of all the instances would serve the request? Because we have so many instances in there. Who decides which is the right instance for the request that's coming in? So all of these questions. How can we solve all these challenges? So this is exactly the reason why we want to introduce an orchestrator tool like Kubernetes. So enter Kubernetes. So as we describe what Kubernetes can do, let's think again about these nodes, right? So we have, let's say we have these 3 nodes, and we need to start placing containers in them. And we have to do a bunch of things to get these containers up and running in the right way. And so instead of having to have an individual person or some sort of a script that needs to run to be able to allocate and to make sure that everything is going properly across these nodes, we're going to be introducing this component called, well, actually a series of components that we call the control plane in Kubernetes. So the control plane has several components that take care of all it's kind of the brain of Kubernetes. So it decides how to schedule the containers into the different nodes. It decides what to do if one of these containers is destroyed, how to bring back one more, how to let them communicate to each other, and a bunch of decisions, right? So for instance, when we want to get one new container deployed to one of these nodes, what we can do is via the control plane, we can create a deployment. So what this deployment is going to do, deployment is, by the way, one of the resources inside Kubernetes. And so what this deployment can do is go ahead, find the image that we need in the container registry, and then allocate what we call a pod for the container that we'll pulling in. Now the pods are really the smallest deployable unit of computing that you can create and manage inside Kubernetes, right? So the pod, it has a similarity to what we call if you think a pod of wells, right? That, I guess that's the symbol for Docker. But it's a group of one or more containers that are sharing storage and network resources. And the pod also declares how to run the containers inside them, right? So you will always be working more with pods than with containers. You can really work with the containers directly. You will always be working with pods. So for instance, in this pod, we will have, let's say, one container, which is a very common case, to just have one container per pod. But you don't have to have one. You can start standing up via this deployment object. You can start standing up more than one container for, let's say this is for our catalog REST API. But in this first node, we don't have to just have this catalog API, right? So we could have some other pod for some other service that in this case has not one, but two containers inside of it. And more than that, we will have also a pod for our Mongo container, right, that we need to also pull in, that has access also to this database. Database needs to get granted access to some storage to be able to store the database files. But then the thing is that these catalog pods don't have to be just in node 1, right? So when we run out of space, we may want to take advantage of other nodes like node 2 here, right? So again, the control plane will take care of deciding where to put these pods across the entire set of nodes that we have here. So in this case, we're just seeing 3, but you can think that this can be an entire farm of tons and tons and tons of nodes, and then control plane will decide which is the node that is the perfect fit for the pods that need to be allocated, right? If deployment declares that it needs 3 pods, so this may be one way that the pods are distributed. If deployment says, no, I need 4 pods, then we may want to deploy yet another pod, pod 4, into node 3, because node 3 is just free at this point, right? Same way with some other pod, it may want to be allocated somewhere else. There's no space in node 1, so let's just put it in node 3, let's say, just because node 3 has so much memory available, right? The other thing is that pod 3, let's say pod 3 wants to talk to actually all of our catalog pods. We want to talk to the database, right? So how do they do that? So there's this object called the service in Kubernetes, and the service allows us to reach the other components that are available somewhere else in the cluster. So in this case, I'm saying, well, I'm going to reach out to the Mongo service, and via that Mongo service, I am actually able to reach to the database. And in a similar way, if we have an external client that wants to talk to our catalog REST API, how can it reach it? So again, we stand up a catalog service, which can be reached in our case, for now, just in the local host, but eventually it could be a public IP. And then this client can reach to this service, and via that service, it can reach not just one, but all of the pods that are running behind this service, right? So it's a way to route to those to those pods. So all of this is what we call, all of these components is what we call the Kubernetes cluster, right? The sum of all these components. And now what I'm showing here is really just the tip of the iceberg in terms of all the possible resources and the series of configurations and the capabilities that can be used within Kubernetes. Really, there's a lot that can be done with Kubernetes, but here we will just explore just a few of them to understand how it works. And so in terms of benefits of using Kubernetes, one of the main things about this is the ability to turn desired state into actual state. So like I said, we create a deployment object where we say, hey, I want 3 copies of the catalog service. So that's a desired state. So Kubernetes, via the control plane, will have to figure out how to make those four instances of the catalog container available as pods somewhere in the series of nodes that we have available. If you have 3 nodes, just find space in those 3 nodes. If you just had 1 node, so figure out how to allocate that in that 1 node. Or we could have hundreds of nodes, right? So turn desired state into actual state is a key feature of Kubernetes. Then, like I said, select nodes to run the pods. So the control plane has knowledge of the stats of each of these nodes. So depending on the amount of CPU or the amount of RAM available in each of the nodes, it is able to allocate the pod in the right place. It also allows for self-healing. And so if it detects that one of the pods, let's say pod 3 is just destroyed for any reason, it should be able to automatically bring back another pod. So let's say that node 2, the entire node just goes down, right? If that happens, then the control plane will know that it is able to, that is missing one node, one pod, and then it needs to allocate that pod somewhere else, either node 1 or node 3 in this case. So this is the self-healing capability of Kubernetes. That's super handy. It also is able to store configuration and secrets. So it has a place to store all the configuration that you need for the services, and also to safely store sensitive information and like secrets somewhere in there so that they cannot be compromised. Like I said, it provides service discovery and load balancing. So when the client comes and talks to the catalog service, it is able to be directed to the right to one of these nodes, following some algorithm to load balance across them. It also ensures no downtime, because whenever let's say that we want to deploy a new version of our catalog Docker image, right, across all of these pods, it will not just destroy all the pods at once and bring back a bunch of pods with a new image. It actually will slowly roll out the new version of the image as new pods as it starts destroying the older pods. So only when it confirms that the new instances of the pods are available, it will start getting rid of the older ones. So that way it makes sure that there's no downtime for our clients. And it can also auto-scale. So Kubernetes can be configured to say, hey, if there's so much CPU being used across all of our nodes, just spin up even more pods in any other available nodes to satisfy the demand. So within this tutorial, we will be doing a scaling exercise manually, but Kubernetes can be also be configured to do this scaling automatically for you. It is able to auto-man storage, so you can easily declare that you want so much storage for your pod, and Kubernetes will, you don't have to know exactly where that storage is going to be. You just have to say, hey Kubernetes, I need storage, and Kubernetes will be in charge to figure out where to find that storage and make it available for the pod. And finally, it provides what we call gradual rollout and rollback. Just like I said, it will gradually start bringing in new pods as needed. And also, if there's some issues with some pods, it is able to roll them back to a previous healthy version. So now that we know what Kubernetes is, let's see how to get our catalog REST API and the MongoDB database deployed into a local Kubernetes cluster. To get started with Kubernetes, the first thing that we're going to need is a Kubernetes cluster. Luckily, if you're already using Docker in your box, you already have an easy way to stand up a simple local cluster for development purposes. Let me show you how. If you go to the Windows taskbar, you should be able to find this Docker icon. You can right-click this icon, select Settings, and this opens Docker settings in your box. I'll maximize this. And here, what you're looking for is the Kubernetes section on the left side, and then enable Kubernetes over here. So I'll just click on it, and then I'll click Apply and Restart, and then click Install. Now, this is going to take a while if this is the first time that you're enabling Kubernetes, because this is going to set up a local cluster, simple with just one node, but still it is a local cluster that Docker needs to download a bunch of Docker images for all the components of Kubernetes into your box, so that may take a while. In my case, I already have all these images downloaded, so it was a bit faster. Once it's complete, what you're looking for is this message here that says Kubernetes running. It should say running and it should be green, and then you know that you're good to go. So I'll just close this window now. With the Kubernetes cluster up and running, one of the first things that I'd like to do is to make sure that I am connected to the correct Kubernetes cluster. And that we can do via the kubectl command line tool, which is the command line tool to interact with Kubernetes. This tool should be already installed for you with your Docker installation, so you should be able to start using it right away. I'll open up a brand new terminal. And what I'm going to do is just type kubectl config current context, hit enter, and that is giving me back Docker Desktop. So indeed, Docker Desktop is the name of the cluster installed by Docker once we enable the Kubernetes cluster. So we are good to go on that side. Now it is time to start creating or declaring how we want to deploy the components into Kubernetes for our REST API and the database. And to do that, we'll need to write a few YAML files. To make this simpler, what I'd like to do is to take advantage of the Kubernetes VS Code extension. So to do that, I'll first just close this terminal, and I'll go to the extensions hub, and I'll search for Kubernetes. This one here should be the first hit. I'll just say install. It should take a few seconds. And now it's ready. So I'll close this. What I'll do now is go back to our file explorer, and I'm going to create a folder to start storing all the files that we need to deploy our resources to Kubernetes. So this is going to be our Kubernetes folder. It can really be any name as you please. And then the first file I'm going to create here is going to be named catalog.yaml. And I'm naming it this way because this will declare all the resources that we need to deploy our catalog REST API to Kubernetes. And also to keep things simple, to speed up the process, I'm going to take advantage of that Kubernetes extension that we just installed to generate a little bit of code here. So I'll just say deploy, and that pops up a little bit of IntelliSense, as you can see. And then we just have to click it, and that will give us a basic shape for a deployment resource. Now, the deployment resource is what you would use to declare the desired state of the containers, or specifically the pods that you want to get deployed into Kubernetes, in this case, for a REST API. So let's understand what this file means. So if you see, the first line declares what we call the API version. This is something that all the Kubernetes resources will have, and this allows you to specify what is the API surface that you want to take advantage of in Kubernetes. So depending on the version that you pick here, you will have access to more or less features of the resource that you're configuring, in this case, a deployment resource. Second line declares the kind, as we know, is a deployment object. And then we go to metadata name. Metadata name defines the name for this deployment. So in our case, we'll just name it catalog deployment. And then we go to the spec section. The first part of this spec section is what we call the selector. And the selector is what we use to specify how is this deployment going to select the pods that it is going to manage. So in this case, it is saying, well, I'm going to manage all the pods that have the following labels. And in this case, we just have one label. It is called app, and then there's a value. The value that we're going to assign here is going to be catalog. So all the pods that have an app label named with the value catalog will be managed by this deployment. So then we keep going into the template section. And so here is when we're going to declare all of these, the containers that are going to be included in this deployment. So one of the first things to declare here is the label or the labels for these for the pods. In this case, we're going to name these pods as catalog. That's going to be the label. So that's the way that we can identify all the pods that are related to catalog in this case. And this one has to match exactly the label that we just typed a moment ago so that the deployment can actually manage these pods. Then we move forward to the most interesting section, which is spec under template. And the first thing that we're going to find here is containers. So here we declare the list of containers that are going to be included in this deployment. And the first thing that we have to do for this very first container is, well, give it a name. So again, to keep things simple, we'll just name it catalog. And then we have to declare which is the image that we are going to be deploying. In our case, we're just going to be using that image that we created in the previous video that we deployed to Docker Hub. And then in my case, it was Julio C catalog B1. So we are saying we are going to be pulling down into Kubernetes this image named Julio C catalog B1. That we were saying there. But you could specify any image that you want here. Next, we go into the resources section. So here's where you declare what resources, specifically in terms of memory and CPU in this case, what resources are needed from the Kubernetes node in order to run your REST API. In this case, I'm just saying, well, I'm going to be needing 128 megabytes, which by the way, 1 megabyte would be equivalent roughly to 1024 gigabytes. And so that's the default value here. You could change this according to your needs. And then on the other side, we have the CPU, where we are saying that we want to use 500 milli CPU. So this is an interesting notation. What it really means is, this is similar to say, I'll just type here, would be kind of like 0.5 CPU. So roughly half CPU, just to understand it better. So 500. So basically, we're saying we are good to go with 1/2 CPU for our REST API, which should be definitely enough for us. Next, let me just scroll down a bit. We have the ports. So here's where we declare which is the port that that our container is exposing and that we can communicate to in order to access the REST API. In our case, we're going to do just as we did in the previous video when we mapped into port 80, because we said that our base ASP.NET Core image overrides our port and by using port 80. So we will be using the same port 80. So that's a port inside the container where we can reach the REST API. The next thing that we're going to need in this deployment is a few environment variables, because if you remember, when we run our container, we had to specify both the host to be able to talk to our MongoDB container, and also the password for the user that connects to that database. So how do we specify environment variables in this case? Fairly straightforward. We can use the env section. So you just type env, and then you have to declare key name value pairs for each of the environment variables. So the first one we're going to declare is the one for host. And then if you remember in app settings JSON, which I'm going to open right now quickly, we have this hierarchy of settings, right? We have MongoDB settings, and in MongoDB settings, we have host, port, user, and password. So I'll go back to catalog YAML, and we have to follow that same hierarchy. So I'll do MongoDB settings. And then the way to separate and to go into the hierarchy in this YAML file will be via double underscore and host. Remember, when we run, when we pass the variables into the container, we use colon, but in this YAML file, the convention we're going to use is going to be double underscore. So that's how you address these different settings. And then we'll give it a value. the value for the host in Kubernetes is going to be MongoDB service. And we'll see in a moment how we define this MongoDB service. But for now, so yes, this is how we can address the MongoDB container that we're going to declare later on. Next, we need an environment variable for the password. But before we can declare it, we actually have to create this password in Kubernetes. And luckily, Kubernetes has this built-in support for secrets, sensitive information like that. So in order to do that, what I'm going to do is just open my terminal, and I'm going to actually use a shortcut here, Ctrl-J. That opens up the last terminal we used. And I'll scroll down this a little bit. And then what I'm going to type here is the kubectl option to be able to create a secret. So that will be kubectl create secret. And then I'll type generic. Generic is a type of secret that we can use in this case, but there's a few other options that you can also use. Generic is fine for us. We'll name it catalog secrets, and I'll use plural just because you can actually put multiple secrets in one of these secrets here, but we're only going to be using one. And in order to type it directly in the command line, what you do is say from literal, and then you actually specify the name and the value for the secret. So the name is going to be MongoDB password, and the value is going to be just like we did before, pass bound word 1, and then I'll hit enter. So that created the secret. Now that we have created the secret, we can actually go ahead and declare it and feed it into an environment variable. To do that, we'll do something similar. So we'll say name, and again, we follow the hierarchy, right? So MongoDB settings, in this case, double underscore is going to be password. And then in this case, we don't want to just type the value, we want to read it from the secret. And to read it from the secret, what we can say is value from, so enter, and we'll say secret keyref. So we're referencing a secret that's named, name is going to be catalog secrets. It's the name that we gave the secret. And the actual key within that catalog secrets is going to be MongoDB password. So that's how you can address a secret from the declaration of an environment variable in Kubernetes. That's looking good. I'll close this terminal again, have more space here. And the next thing that we want to specify here is our health probes. So the health probes is the mechanism that enables Kubernetes to constantly monitor the health of our REST API by using the health checks that we already defined. So if you remember a few episodes ago, we declared some health checks in the REST API. So now is when we can actually use them to let Kubernetes know if our containers are in good shape or not. And if you remember, we had both a liveness and a readiness probe. So both of them we're going to be using here. So I'll start with the liveness probe, and to declare it, what you can use is liveness probe. And then the kind of probe, there's a few kinds of probe, and what I'm going to be using here is the HTTP get type of probe, which is just going to call some HTTP path with the get verb into the API. And so the path that it needs to use is, if you remember, that would be held live, and it needs to use port 80 for that one. And that's it. That will be the liveness probe. And I'll just copy this to define our readiness probe. The readiness probe is going to be very similar, but it ends in ready. So if you remember, we would use the liveness probe to tell if our REST API is up and running, and the readiness probe to tell if any dependencies of the REST API are responding correctly and are ready, and basically the REST API is ready to serve requests. So with that, we have properly declared a deployment for our REST API, but it is not enough. So this will go ahead and create the pods, pulls the containers, and with environment variables and all that, but still there's no way to reach, for anybody to reach into this container from the outside. And to enable that, we need to bring in another component that's called service. So that service we could either create in another YAML file, or we can just declare it right here, which is what I'm going to do. And the way that you separate these two different resources in the YAML file is by using 3 dashes. And then you can go ahead and start declaring your resource. So I'll do some IntelliSense again here. So I'll just type service, and that brings up the Kubernetes service IntelliSense here. So I'll click on it, and that will scaffold a little bit of pieces in there that we can take advantage of. So, so the service is the type of resource that you use to be able to address a resource within Kubernetes, either internally or externally, which is what we need at this point. The service we need to give, we also need to give it a name, just like we did with deployment. So we'll name it catalog service. And then one piece that's not listed here, but that is important for us, is the type. There's a few types of services, but in our case, we want to use a type named load balancer. Load balancer is the one that allows Kubernetes to request an actual IP or an actual, or not, I guess not an IP in this case because it's localhost, but it requests a way to open kind of a window to the outside, so that people can actually reach out to our REST API from the outside. So we'll see how that name resolves when we run this. But yeah, load balancer is the one that we need to use. Otherwise, we cannot reach the service from the outside. For selector, we have to specify the pods, the label for the pods that we have declared before. If you remember, these pods here, when we declared the template, we said that the label for all the pods that are going to be managed by the deployment is going to be catalog. So that same label is the one that we have to use when we declare the service. When we declare the selector, we're going to say, well, we're going to, this service is going to be able to target any of the pods that have the app label with the value catalog. So that's how you connect the service with the pods. And then you also have to specify, okay, so which is going to be the port that from the outside, the people can reach into our API from the outside, and that has to be mapped into a port in the container. So that port, in this case, is going to be, we're going to be using just 80, just because it's the default port for HTTP. So that will allow our clients to not even have to specify a port. They will just be able to just go directly into the API. So they will go into port 80, and the target port has to be the port that we have specified for the container. So remember, over here in ports, we declared container port 80. So container port 80 is the target port that we want to use here. So it's really mapping 80 to 80, but it doesn't have to be like that. We could have said, let's say 8080 maps to 80. That would be totally fine, just like we did with the container. But it is more usual to just say port 80. So now we should be ready to start deploying these, to deploy both these resources, both deployment and the service. So how do you deploy this into Kubernetes? So we have to go back to our kube control tool to be able to do that. So I'll open up my terminal again, Ctrl J, and I'll switch to my Kubernetes directory. The command to apply this deployment is, this YAML file is kube control apply -f and then the name of the file. Hit enter, and you should get a couple of messages stating that the deployment has been created and the service has been created. Now, if you want to see which is this deployment or what's the state of the deployment that should be created, what you can do is just say kube control get deployments, and that will give you a list of all the created deployments. In this case is saying we have one deployment named catalog deployment, and currently it is saying that 0 of one of the pods is ready to go. So it means that it is not really ready yet. And so let's dive in a little bit more and get details about the actual pods that got created. So what we can do is say kubectl get pods. And so as you can see, all the one pod that we have declared here, the name starts with the name of the deployment, and then it gets a name for what we call the replica set, which we will not talk about in this video. And then finally, some identifier for the actual pod. And then indeed, the pod is not ready. So this is saying 0 of 1 pods are ready to be used, right? To be reached by the outside. But still it says running. So this means, what this really means is that our liveness probe, right? You remember we have a liveness probe, is reporting a healthy status, but our readiness pod is not reporting a healthy status. So to find out a little bit more of what's going on here, and I'll expand this a little bit more, let's actually get some logs from that catalog pod. So kubectl logs, and then the name of the pod, hit enter, and then we're seeing something interesting here. Let me scroll up a little bit. Yes. So here, as you can see, our MongoDB readiness check is failing with status unhealthy. The operation was canceled, and as you can expect, this is this is totally expected because we have not really deployed any database yet. But this is great. This confirms that our readiness health check, both health checks are actually working properly. And we just need to make sure that we fix this problem with the database. We bring it up, and then we should be able to have a REST API up and running. Let's close the terminal, and let's actually declare what we need to declare for our database. So I'll go back to my Kubernetes directory, and I'll say new file. And this file is going to be called mongodb.yaml, because everything we're going to declare here is just for the deployment of that MongoDB database. Now, the type of resource that we're going to create for MongoDB is actually called a stateful set. And since we don't have a way to generate the skeleton for a stateful set yet, we're going to use the deployment template for this. So let's just do deployment, select Kubernetes deployment. And then what I'm going to do is just switch from deployment to stateful set. So a stateful set, it has similarities with a deployment, but it is actually meant for stateful applications. So a stateful set provides guarantees about the ordering and uniqueness of pods. So when you see the pods that are created by a stateful set, they will not have random names. They will actually have some very specific ordered names. So for instance, in the case of this one, it may be called MongoDB 1, MongoDB 2, MongoDB 3. And more than that, if one of these pods dies, let's say MongoDB 1 dies, and when it comes back, it will come back as MongoDB 1 once again. And this is pretty important in the case of MongoDB because we will attach a persistent volume to it, which will have the database data files. And we want to make sure that those files don't just get lost as the pod is reconstructed in the case that it needs to be killed for any reason, right? So we want to keep it around. So the right type of resource to use for a persistent service like MongoDB would be a stateful set. So just like we did with the deployment, one of the first things to do here is to assign a name to the stateful set. In this case, we will name it MongoDB stateful set. And then one important thing that's not being generated here is what we call the service name. And this service name is used to give some identity both to the stateful set and to the pods that are going to be managed by it. Which is not actually needed for deployments, but for stateful set, it's a requirement. The name that we're going to give here is MongoDB service. And we see how this service is tied later on to the MongoDB service and back to the catalog later on. Then also, just like we did with the deployment, we need to define which are the labels that the stateful set is going to be using to select the pods that it's going to be managing. So in this case, let's say that our pods are going to have the MongoDB value in its app label. And if we're going to do that, then we have to make sure that in the pod template down here in labels app, we have to be using the same value. So all our pods are going to have an app label with a value of MongoDB, and then the stateful set is being configured to manage all those pods with the MongoDB value in the app label. Now we keep going down into the container section inside the spec, and then let's just give the name of the container. Let's name it again MongoDB. And then for the image, we'll use the same image that we've been using so far. It's just Mongo, latest version of Mongo. Then we keep going down into the resources section, and we will leave these resources. They should work just fine for us, but it's up to you to modify how much memory and CPU you expect to be using for your MongoDB server and your MongoDB database. Moving on, we have to declare the port where the MongoDB container is listening on. And by now we know that this port is 27017, right? So that's the port that we have to use to connect to the MongoDB service inside the container. And once again, like we did with catalog YAML, we have to define a couple of environment variables to be able to talk to to be able to start up our MongoDB container. And those are the username and the password for the user configured for MongoDB. So let's declare an env section. And here let's start declaring, so the name of this environment variable is Mongo initDB root username. And the value that we're going to assign to it is the one that we're using so far, MongoAdmin. And then for the password, we're going to be using really the same secret that we use in catalog. So I'm switching to catalog here, and I'll just copy our password section into MongoDB, paste here, and fix indentation. And then as you see, we're reading from the same location, but the name of the environment variable is just a little bit different. It's going to be Mongo initDB root password, right? So that's a username and password environment variables that the MongoDB container is expecting. The next thing that we need to define in the case of the MongoDB container is what we call a persistent volume, right? So we need to declare some storage. We need to ask Kubernetes for some storage space to place the data files for our database. Otherwise, I mean, yes, a database will exist within the MongoDB container, but when the container and the pod that contains this container is killed for any reason, the data will just disappear, right? So we don't want that to happen. So to do that, we create what we call a persistent volume. And to create this persistent volume, we're going to use what we call as a volume claim template. So let's do that. And let me make sure I pick the right place for this. Yeah, it should be here. So let's say volume claim templates. And really the volume claim templates is a way to declare or to ask Kubernetes for some space, some storage space in the node where the pod is going to be executing, right? So I need some space, and we have to declare some details about that space that we're going to reclaim. So first we're going to set up some metadata. And we pretty much just need the name here. So what's the name that we're going to give to this volume? That's going to be data. And then we have to specify the specifications for the volume that we're going to ask for. So that goes into the spec section. And then here we have to specify an access modes. So access modes declares which way is this persistent volume going to be mounted into the node. And actually this should go in the previous line. So do it like this. And for our case, the mode of read write once should be good enough. And really this one here means that the volume that's going to be created, that's going to be mounted, is going to be mounted as read write and for a single node. So meaning that just one node can read and write to this volume at a time. If you wanted to have more than one node be able to write to this volume, you will have to use a different kind of access mode. And then finally, we have to define the resources that we need here. So in this case, we'll declare resources and then requests, and finally storage. And here's where we declare how much space we want for this volume. And for our case, let's go for one. I think the term will be GB byte, similar to 1 gigabyte. That's going to be as much storage that we're going to reclaim for this volume. We'll save this. And so with this, we have reclaimed space in the node, right? For this for MongoDB. However, we still need to tell our container that such a space exists, and we have to map that space in the host machine to a space into the container. And to do that, we're going to declare a volume mount. The volume mount needs to be declared inside the container spec. And so I'll just type here volume mounts. And here we're going to specify a name for it, and this name will have to match exactly the name that we have specified in the volume claim template, right? So we said it's going to be data, and so data is the name that we should use here. And then the mount path is the path where traditionally MongoDB stores its data files, right, inside the container. So that space is going to be /data/db. So what this really means is that when MongoDB container writes into its data.db directory for the data files for the database, those files are going to end up into the persistent volume that has been declared on this side here, right? So the data gets written outside of the container and into the persistent storage in somewhere in the host. So this way, if the container goes down, if the pod goes down for any reason, the data is not lost, and it will come back as the pod comes back with the same identity in this stateful set. The next thing that we need to do, just like we did with catalog YAML, is declare a service, right? A service that allows us to address or to get to this MongoDB service. And so I'll just do this, and then I'll type service for Kubernetes service. So it generates just like we did before. And just like before, we have to specify some name for this service. Let's call it MongoDB service. And then one important and missing piece here is this thing called the cluster IP. So cluster IP is what you would use to specify the IP address for your service, right? And so by default, any service will get a local IP that can be used to talk to other services within the cluster. But in our case, what we want to create is what we call a headless service. So we don't want to assign an IP to the service because in a stateful set, we want to address each of the nodes, each of the pods individually. So in this case, we're going to say none. So we don't want an IP in this case. So it turns it into a headless service. Now for the selector, once again, we have to specify how is this service going to be mapped into the pods that exist for MongoDB, right? So for that, we have to go back, once again, into the pod template. So pod template, metadata labels, app. The label that we're looking for is app, and the value is MongoDB. So we go back, copy that into the selector, MongoDB. So anytime a request comes into this service, it will find the nodes that, the pods that have been tagged with the MongoDB value in the app label, and then that's how it is going to find them. Finally, we need to specify the ports, and so just like we did with the container, we're just going to do a simple mapping of 27017. So any request that comes into 27017 should be redirected to the port where the container is listening on, and that port is, again, as you can see here, 27017. So just copy that over here. Now that we have done this, it should be ready to get started with this MongoDB container. So I'm going to open up my terminal again, Ctrl-J, opens terminal. I'll scroll down this a little bit, and then I'm going to switch to the Kubernetes directory. And here I'll just do kube control, apply, -f, and then our YAML file, MongoDB YAML, and I'll hit enter. So both the stateful set and the service have been created. And so at this point, let's see how does this stateful set look like, right? So let's do kube control get stateful sets, and that gives us the one stateful set that has been created, MongoDB stateful set, which seems to be ready. It's healthy, it's in good state, and it's ready to be used. Now that we did that, let's take a look at all the pods that we have right now. So once again, kube control get pods. And as you can see, now we have our catalog pod. It is actually ready. So it's no longer reporting 0 of 1, it's reporting 1 out of 1. And that is because the readiness probe that was trying to reach into our MongoDB database, it is now able to actually do it. And that's because we now do have the MongoDB service available. If you remember, when we were in catalog YAML, we declared that the MongoDB settings host was going to be MongoDB service. It was not available yet, but now that we have declared it and we have deployed it, we do have the MongoDB service that I can reach out to, and then that allows our health check to pass. So we can connect to the database successfully. And just like we have that pod, we also have the pod, the MongoDB stateful set 0. So as you can see, it is not a random ID as it is in the case of the deployment. It's more of a very specific numbered and ordered index for these stateful sets, right? So if it dies, it needs to come back with that same number. Let's now see if our REST API is working properly now that it's running within Kubernetes. So let's open up Postman. And last time that we did a get against our REST API, we did it over port 8080, so because that's the port that we exposed when we run it is as part of Docker. But now we have to switch to port 80. And we can either query the API like this, or we can just remove 80 because it's a default HTTP port. So this should be good enough to do a get against the API. So let's see what we get. And sure enough, we don't get any results because remember, this is a brand new database that is now hosted inside Kubernetes. So it's expected to not have any data, but we can go ahead and create something in there. And so I'm switching to the post tab here, and I'm going to also change this to just be HTTP localhost items. And then for body, let's come up with something quickly. So let's say we're going to create a potion again, price 12, and then hit send. And sure enough, the potion has been created. We can create yet one more thing. Let's say an antidote with price, let's say 17, hit send, and has been created too. We go back to the get, hit send, and we are getting our 2 items now. So the REST API is working properly, but everything is now running within Kubernetes. And so we talked about this capability of Kubernetes to self-heal. Right? So it should be able to always enforce that desired state, regardless of what happens to the pods. So let's see how that exactly works. So I'm back in VS Code now. And what I'm going to do is just to get a little bit more space here to be able to visualize things better. So I'm going to move this left side all the way to the left. And then what I'll do is I'll spin up another terminal with the split terminal button so that now we can have 2 terminals side by side, and I'll move things around a little bit like this, perhaps right there. And so what I'll do is on the left side, I'm going to be watching for the pods with kube control get pods -w. So that lets me see any changes that happen across the currently existing pods in there. And on the right side, I'm going to simulate the killing of one of these pods. So let's say let's imagine that the pod had some bug and that causes the pod to crash, right? Then what happens? So let's do kube control, delete pod. And so let's try our catalog pod, our only catalog pod. And I'll go ahead and delete it. So I'll hit enter and see on the left side how right away, as soon as it starts terminating that pod, it immediately starts spinning up a brand new container, right? So that's the capability of Kubernetes to always detect this discrepancy between the desired state and the actual state. And as soon as it detects the situation, it needs to do whatever needs to be done to bring back things to consistency, right? So in this case, the new pod is up and running, and then I'll just do Control C and I'll do get pods again without the W. And you can see that now we have again our 2 pods, but now we have a catalog pod with a different identity, right? You can see it's not the same identity as before. And that's because deployment type, the deployments create pods that are ephemeral in nature, right? So they are just stateless. Now, that's not the same case as for our stateful sets. As we said, our stateful set should be persisting across the lifetime of a pod, right? So if we just have this MongoDB stateful set 0 here, what happens if we delete it? Right? More than that, what happens with the data that is being held by this MongoDB pod? Because we already have data in there. So would it survive? Would the data just still be there? Will the pod come back? So let's try it out. So I'll wash again for the pods, and I'll copy the name of our stateful set. And so I'll do kubectl, kubectl, delete pod, and I'll do MongoDB stateful set. Let's see what happens. And see on the left side, the pod is indeed getting terminated, but right away, Kubernetes detects that it needs to bring it back. And it needs to bring it back with the same identity, MongoDB stateful set 0, because this is a stateful set, right? And we don't want to lose the data that's being held by this pod. And in fact, if I just Control C this and I'll do get pods, we have our 2 pods, and now we should be able to verify that the data is not gone. So it should still be there. So if I go back to Postman and I query for the data once again, we can see that the data is still there. So it has not gone anywhere. So that means that indeed a persistent volume got created and the data is being stored outside of the container and into the host. And that's enabled by our stateful set. So I'll go back to VS Code now. And we also talked about this capability of Kubernetes to easily scale the pods and the containers inside them without really much trouble, right? So if we out of nowhere, we have much more requests in our website, and we need to have not just 1 pod for catalog, but we need to have 3. What would we do? How can Kubernetes help us with that? So once again, let's monitor what's happening on the left side, get pods. And then what I'm going to do here is just ask Kubernetes to scale the deployment. So to scale the deployment, what you can do is kubectl scale deployments, and then it will be catalog deployment. And then you have to say how much, right? Right now we have 1. Now we want to have 3. So I'll hit enter. I notice on the left side that it immediately starts provisioning a bunch of new pods to enforce this new decided state, right? And this happens blazing fast, right? So if I just do Control C now on the left side and get pods again, you can see that we already have 3 pods where we only had 1 just seconds ago. So here you can tell like the power of the combination of Docker containers and Kubernetes, right? How we can bring in much more instances of our containers, of our REST API in this case, without really much trouble. Just running 1 line, we now have 3 copies of the container running. And now the whole point of having these 3 replicas of the pods is so that we can do some good load balancing between them, right? So when a request comes, it should land in one or another of these pods. And how can we verify that? Well, unfortunately, we don't have a good means to do that right now, but I think we can easily introduce a little bit of logging into the pods so that we can easily tell to which pod the request is landing in. And so to do that, what I'm going to do first is I'll just close the terminals for now. And then I'll go to our Explorer, I'll go to our items controller. And here I'm just going to add a little bit of logging. To add logging, what we can do is bring in the standard iLogger interface. So I'll do read only iLogger of items controller. And let's call it logger. And so iLogger is a standard object available in .NET 5, so pretty much in any application .NET 5. And so what you can do here is just do dependency injection as you do with any other service, built-in service of .NET 5. And I'll capture the logger instance right here. And now that we have that, what we can do is just pick one of our APIs and do some logging. So I'll go for the easiest one, which is going to be our get items API. So in this case, I'll just open up here one line, and I'm just going to log a little message that says how many items we found, right? So to do that, what I'll do is just logger.log information. And then let's do a little bit of string interpolation here. First thing I'm going to put here is the current time, and I'll do that via the datetime class. I'll use the UTC time to string, and then we'll show just the time in the format of hours, minutes, and seconds. Okay, so time formatted there, and then I'll just do colon, and I'll just say retrieved items that count items. Okay, so just for us to verify that things are landing in different pods. So I'll save this, and then with that change, what we have to do now is to create a new version of our Docker image. So I'll open up our terminal now, and I'll delete one of these so that we only have one. And here I'll do what we did in the last video. So I'll just run our docker build command, and I'll be publishing this into Docker Hub. So I'll keep using the same format as before, using my username first, and then the name of the image. And then the one thing that I'm going to bump here is the tag, because this is a new version of the image, so we should be bumping it, let's say, to V2. This is necessary so that Kubernetes can later tell that this is a new image and that it needs to pull it down from Docker Hub. Otherwise, it will not be able to tell. So then I'll say dot. I'll hit enter, and then I'll just miss one parameter here, which is the -t for the tag. Hit enter again, and this is going to build the image. It's going to reuse some of the cache layers, and then it's going to build just the piece that is needed. Okay, so the image is built. Now I'm going to do I'm going to log in into Docker Hub, Docker login. And now I should be able to just push the image over there. So I'll do docker push, would you see catalog v2, hit enter. And then again, some of the layers are going to already exist in Docker Hub. So only the layer that's missing, which is my little change of one line of change here, is the one that is included in this image, and is the one that needs to be pushed into Docker Hub. Okay, so with the image in Docker Hub, we should be able to tell Kubernetes that we want to start using it. So for that, I'll go back to catalog YAML, and I'll say, hey Kubernetes, I don't want to keep using the image version 1, I want to use version 2. Save that, and then back in the terminal, I'll switch to our Kubernetes folder. And here, I'll just apply this file once again. So kube control, apply -f, and then we'll do catalog YAML. Okay, and so now if we do kube control get pods, let's watch, see what's happening. And so as you can see, the old containers, the old pods are getting destroyed, and new pods are getting immediately being stand up for the new image version that we need to be using. So this should take just a few seconds. And so I'll Control-C now, and I'll see the actual status of the pods. Let's see what we got. So yeah, so we have 3 new copies of our catalog REST API, 3 replicas of the pod. And so now we should be able to tell if we are load balancing across them. So to do that, what I'm going to do is, again, I'll just make some more space here. I'll expand this terminal, perhaps even more. And I'll split the terminal now in 3 so that we can tell the logs of the 3 pods. So first here, and I'll go back one directory, and I'll say kube control get pods, so we get the names of all the pods. And then I'll do one by one. I'm going to do keep control logs for this one, and then I'll do -F so that we can tell the logs. And then I'll do the same here. So which is our second pod? Let's take a look. It's going to be this one here. -F. And then the third one is this guy here for our third terminal. Keep control logs -F. Okay, so now we're tailing the 3 pods, and I'm going to go back to Postman, and perhaps we can accommodate this into here, just on top of the other one, to see what's going on. Yep, and yeah, so one more thing actually that we have to change in Postman is our headers. Let me actually maximize this for a moment, because the default behavior of Postman is that it's going to send this connection header with the value of keep alive. And what that's going to do is actually set up a persistent TCP connection between Postman and our pods. And that will actually prevent our little exercise from allowing the subsequent connections to go into different pods. So just for our testing purposes and to see how things work, I'm going to disable that header here and see how these things work. And yeah, so with that, I'll minimize this in this way, and let's send one request and see where it lands. You see it landed in our first pod on the left side, retrieve 2 items at 7:04:52. Let's send again, and now it landed in our second pod. Let's send again. Oops. Again in the second pod. And then at this point, it's going to be a little bit random. I mean, the algorithm that's supposed to be using is round robin, but really things can land in any pod at this point. So there you go, load balancing in Kubernetes, fairly straightforward, without you having to do really much work on it. And if you scale into dozens of pods, then all of them will be serving your requests appropriately. And so that's it for this video. And I hope, as usual, it was useful. And if you have any questions or any comments, feel free to leave me a note here in the comments. And consider hitting the like button if what you're seeing here you think there's value on it. And don't forget to subscribe if you'd like to know right away when I publish any new videos. Thanks for watching, and I'll see you next time.